Group theory. The term group was used by Galway around 1830 to describe sets of one-to-one functions on finite sets that could be grouped together to form a set closed under composition. The outlines of this lecture: at first, we give definitions and examples of groups. Second, we define the order of groups, elementary properties of groups. At first, a binary operation. Let G be a set. A binary operation on G is a function that assigns each ordered pair of elements of G an element of G. This condition of assigning an element of G to each ordered pair of G is called the closure of the set G under the given binary operation. Example: addition, subtraction, and the multiplication in Z, the sets of integers, are binary operations. Division in Z is not, since the division of 8 and 3 not belongs to the set of integers. Groups. Let G be a non-empty set and star be a binary operation defined on it. Then the structure consisting of a pair of a set G and the binary operation star is said to be a group if the following axioms are satisfied. Closure property: A star B, or the composition of A and B, belongs to G for all A and B belongs to the set G. Associativity: the operation star is associative on G, i.e. A star of B star C equal A star B all star C. That's for all A, B, and C in G. Existence of identity. The third condition: existence of identity. There exists an ionic element E belongs to G such that A star E equal A equal E star E, that for all elements A in G. E is called the identity of the binary operation star in G. Existence of inverse. For each element A belongs to the set G, there exists an ionic element B belongs to G such that A star B equal E and B star A equal E. In this case, we call that the element B is the inverse of the element A. The element B is called inverse of element A with respect to the binary operation star, and we write B equal A sub minus 1. Abelian group. A group G is said to be abelian or commutative if the equality of A star B equal B star A for all two elements A and B in the set G. Examples. One example. The set Z of integers, Q of quotient, and R of real numbers are groups under addition with identity 0 and the inverse the minus A for A. None of these are grouped under product, since one is the multiplicative identity and so 0 has no inverse in each case. However, Q star, which is Q without the 0, and the R star is the real number without the 0, are groups under the product. But that star is the set of all integers without 0 is not a group because every element has no inverse. The integer number 3 has no inverse. The set of complex number 1 minus 1 I minus I is a group under complex multiplication. 1 and the minus 1 are their own inverse, i.e. 1 is the inverse of minus 1 and the minus 1 is the inverse of 1. And the I and the minus R are inverses of each other. The table of such a group is given by, so that 1 product 1 equal 1, 1 product minus 1 equal minus 1, 1 product I equal I, and so on. Minus 1 if it's a product with 1 minus 1 I minus I, we have this row. I product 1 I minus 1 minus I, and so on. In this case, we have that 1 is the inverse of 1 because 1 product 1 induced the identity element. Minus 1 is the inverse of minus 1 because their product implies the identity I and the minus I are their inverse of each other because the product of I and the minus I induce the identity 1, and so on. Let M be the sets of square matrices of 2 row and 2 column, where the elements are real numbers. The binary operation of addition given by, if we take 2 elements of this set, the addition is given by this equation. M is a group with the operation with this operation, where the 0 matrix is the identity and the inverse of this matrix is this matrix. The determinant of the square matrix A is given by det A equal A product D minus BC. So consider a set call it GL2 and R, consisting of square matrices A, B, C, D, where A, B, C, and D are real numbers, such that the determinant not equal 0 of this matrix, with multiplication given by. If we multiply this matrix with this matrix, as we know, multiplication is closed in the set GL2R, since the determinant of A product B equal determinant A product determinant B. Associativity is true. The identity is the identity matrix. The inverse is given by the inverse of the matrix A, B, C, D is given by this form. Then this set is a group under multiplication. An example of binary operation on the set of integers of congruence module n. On the set of all congruence classes module n, Zn or Zn, which consists of the equivalence classes 0, 1, 2, 3, to n minus 1. The addition and the multiplication defined by addition of the two congruence classes A and B equals the congruence class of A plus B. The product is defined by the product of the two congruence classes A and B equals the congruence class modulo n of A dot B. Example: the system consisting of the set of all congruence classes modulo 6 and the addition is a group, which given by 0 addition 0 induced 0, 0 addition 1 induced 1, 0 addition 2 induced 2, and so on. 1 addition with 0 induced 1, 1 which added it to 1 induced 2, 1 and 2 induced 3, and so on. Example 6. The system consisting of the sets of congruence modulo 7 and the product is a group. If we product the congruence class A1 with congruence class of 1, we have the congruence class 1. If we product congruence class 1 with 2, we have 2. The product of 1 by 3 induced 3, by 4 induced 4, 5 induced 5, by 6 induced 6. The congruence class 2 product with 1 induced 2, product with 2 induced 4. The congruence 2 if it is a product with 3 induced 6. The congruence 2 induced by 4, product with 4 induced 1. And so on. This is a group. Order of a group. Order of a group and the order of an element of a group. Order of a group, the number of elements of any finite group is called the order of a group. It is denoted by O of G. The order of a group is the number of its elements. An infinite group is a group of infinite order. For a finite group, the order is the number of its elements. In an infinite group, its order is infinite. Let G is a group of two elements 1 and -1, then G is an abelian group of order 2 with respect to multiplication. The set of integers is an infinite group with respect to the operation of addition, but this is not a group with respect to the multiplication. So that the order of such a group is infinite. Order of an element of a group. Order of an element of a group. Let G be a group under multiplication. Let E be the identity element of G. Suppose A is any element of G. Then the least positive integer n, if exists, such that A sub n equal E is said to be order of the element A, which is represented by order of A equal n. Since n, A sub n equal E when A sub n equal E, n is called the order of A. In case such a positive integer does not exist, we say that the element A is of infinite order or zero order. So if one asks when an element is said to have infinite order, the answer is if such positive integer n does not exist. The multiplication group J consisting of the four complex number 1 minus 1 I and the minus 1 of the first roots of the unity have order of its elements. The order of 1 is 1. The order of minus 1 is 2. Why? Because minus 1 squared equal 1. The order of I is 4. The order of minus I is 4. The additive group of integers, since 1 product 1 equals 0, the order of 0 is 1, finite, but n dot a not equal 0 for only non-zero integers, so the order of a is infinite. Elementary properties of groups. Uniqueness of the identity. The identity of a group G is unique. Proof. Suppose that E and E dash are two identity elements of G. Then E product with E dash is equal E, since E dash is the identity. And the E product E dash equal E dash if since E is the identity. So that's E equal E dash. Cancellation law. In a group G, the right and the left cancellation laws hold that B product A, if B product A equals C product A implies B equals C, and if A product dot B equal A dot C implies that B equals C. To prove that, suppose that B product A equals C product A and the little a dash be an inverse of A. Then if we multiply this equality by the inverse from the right, A dash product BA, A dash product with CA, we use the associativity P A product A dash equals C product A dash. A product A dash implies the identity by the associativity. So we have P E equals C E, and the E is the identity element. Then we have B equals C. The proof of the left cancellation is similar. Uniqueness of inverse. The inverse, if it exists, is a unique element. For each element A in a group G, there exists a unique B belongs to G such that A dot B equal B dot A equal B. In this case, B is the inverse. Proof: suppose that B and C are two inverse of A. If B is the inverse of A, then A dot B equal A. And if C is the inverse, then A dot C equal B. This implies that the right side of two equality is E, so we have AB equal AC. By the cancellation law, we have that B equal C. In a group G, the inverse of A product B equal the inverse of B product with A, the inverse of A. Since the inverse of A product B is the inverse of A product B, so we have that the product of two elements implies E. And A product B product with inverse B product with inverse A, that's equal by the associative condition. We take P product with B minus 1. This product implies the identity. So we have A, B product with B minus 1 induced E and A minus 1. The E product with E implies A. So we have that equation induced A product with A minus 1 and all induced E. So that P minus 1 product A minus 1 is the inverse of AB. Here, AP minus 1 is the inverse of AB. Then we have that AP all minus 1 equal B minus 1 product with A minus 1. Since the inverse is unique, then we have that A P all minus 1 equal B minus 1 A minus 1. Thank you for listening.